Alright, so we're moving on to forces now, and this is actually going to be a little bit more cruisy than what we have been doing, so you'll be able to enjoy today's lesson. This here is my ambulance, and it is currently parked up there, and it is stationary, so it's not moving forwards, backwards, up or down. And we'll add the force arrows on. This here is the center of mass, and down here we'll make it 2 centimeters long. So I've measured from there to there. There is called force support. Nope, we'll call it force weight. Because it's pointing down, that is force weight. This one pointing upwards, which is exactly the same length, 2 centimeters, is going to be the force support. So pointing up, force support, pointing down, force weight. And notice that I've aligned both these arrows so that going through this point here, which is the center of mass of the object. So if you were to balance this ambulance, that would be its balance point. So if I was to put it there, it would balance around that point. If I was to put it here, I could balance it all through the center of mass of the ambulance. Because it's stationary, that means it's got no forward thrust force or any reverse drag force acting on it. It's just stationary. So that diagram is complete. Now we've got it traveling at a constant velocity. It's still going to have the same weight force going down, which we'll just call force weight. And it's going to have the same force support, which we can call Fs. But now that it's going at a constant velocity, the engine's creating a forwards thrust force. So that's going to be force thrust. And because it's not accelerating, that means that the force acting from behind, which should also act through the center of mass, is going to be force of friction or drag. I think your SciPad refers to it as drag most of the time. Oh, maybe friction. Force friction. Okay, because the length of that one and the length of that one are exactly the same, and because that one and that one are exactly the same, that means that it's traveling at a constant velocity. There is no acceleration. All right, now we go to accelerating. So the driver here has put foot on accelerator, and that has increased the thrust force. So I'm going to make that one a bit longer. And so that's force thrust. And the drag or friction has stayed the same. So there's still the same length going backwards. Force of friction. And we've still got our same force weight. And equal and opposite to that, we have got our force support. So that there is an example of it speeding up like that. Now, this one is unfortunate things happened, and our ambulance has travelled through some quicksand. So our force weight is going to be the same, 2 centimeters as what it always was. So we'll measure that one down. Force weight going down. The problem though is that the support force is no longer as much as what it was. So we're going to draw the force support a bit shorter. Force support. And we'll say that he's tuned off the engine and he's just stuck. So he's got no forward movement and no friction. He's just parked up in some quicksand, and he's currently accelerating downwards into the quicksand, which is not a nice thing to happen. It's a bit sad, actually. Alright, we'll just do some calculations around this one. So if the support force on this ambulance was 2,200 newtons, and because it's not accelerating vertically at all, that means that the force weight must also be 2,000 newtons. So those two are equal and opposite, and they cancel out. There's no net force in the vertical direction. However, because it's accelerating, it's got 1,800 newtons trying to make it go faster. The friction's got to be less. So we'll say that it's only got 1,200 newtons of friction. That means that the net force, so force net, is equal to 600 newtons. And that's the size of the force that's causing it to accelerate. So in our next lesson, we'll start using that number to do some calculations. But this should be enough for today.